So friends, now in this section we are going to talk about areas of quadrilaterals, and we are going to find the areas of these quadrilaterals which are specific in nature with the help of the areas of triangles which we have learned in the previous sections. So now if you can imagine a quadrilateral, a general quadrilateral, right? So this quadrilateral, if I connect the diagonal, basically if I connect two opposite vertices and form a diagonal, then as you can see, this quadrilateral is now broken into two different triangles. So now if I individually find out the area of one triangle and add this area with the area of the other triangle, then eventually I'm going to get the area of the entire quadrilateral. So basically using this concept that a quadrilateral is nothing but two triangles. So basically the concept being the area of the quadrilateral is nothing but the area, or rather the sum of the area of the two triangles. We are going to find out the area of a rhombus, the area of a trapezium, and the area of a general quadrilateral. So let's start with the rhombus in general. So this is a rhombus A, B, C, D. As you can see, this rhombus has AC and BD as its diagonals, and as we know, a rhombus has its diagonals as the perpendicular bisectors of each other. So basically where the point O, basically the diagonals are meeting at point O, that point is 90 degrees, and that is a fact which we are going to use. So the area of this rhombus ABCD is nothing but the area of triangle ABD plus the area of triangle BCD. As you can see, this rhombus is separated in two parts. One is the upper triangle, the triangle ABD, and the lower triangle, triangle BCD. So as I said, we are going to use or bank upon the concept that a quadrilateral, area of a quadrilateral is nothing but the sum of the areas of the two separated triangles. So let's individually focus on each of the triangles. So now area of rhombus ABCD is equal to area of triangle ABD plus area of triangle BCD. Now area of triangle ABD is nothing but half into base into height. So in this case it is half into BD into AO, because the corresponding height now for triangle ABD's base BD is nothing but AO, because AO is perpendicular to BD. Now similarly, area of triangle BCD is going to be half into BD into OC, because OC is the corresponding height for the same base BD for the triangle BCD, and hence the area of rhombus is nothing but half into BD into OA plus half into BD into OC. Now we can take half into BD common out, then what is remaining in the brackets is OA plus OC, and as you can see from the diagram, OA plus OC is nothing but AC, which is the length of the other diagonal. So the bottom line, we can say that the area of a rhombus is nothing but half into BC, half into BD into AC, which is nothing but in a general form half into product of its diagonals, and that is what we had learned in the previous chapter as well. There we had only mentioned the area of a rhombus being half into D1 into D2, where D1 and D2 are nothing but the length of the diagonals. So we can write the area of the rhombus as half into product of its diagonals. So this forms area of a rhombus. Now let's go to the second specific quadrilateral. As I said, let's talk about a trapezium in general. So here is a trapezium. This is trapezium ABCD. As you can see, the basic property of a trapezium is opposite sides are parallel. So in this case, as you can see, AB is parallel to CD, or AB is parallel to DC, as you can say. AB is the bigger side, and the length of that side let us take as B, small b. Let us take the length of CD as small a, right? And let us take the perpendicular height in this case, let's drop perpendiculars from points C and D onto the base AB. Let the perpendicular from D on AB be at point M, as you can see, and the other perpendicular from C onto AB be at point N. So this is the diagram of the trapezium which we are talking about. CD is A, small a, AB is small b, H is the height. Now, as you can see, after the perpendiculars are dropped, this particular quadrilateral, or specifically trapezium, is broken into three parts. There is a triangle AMD, to be specific, there is a right angle triangle AMD, there is a quadrilateral, or again to be specific, there is a rectangle MNCD, and there is another right angle triangle CNB. So this trapezium has been broken into three parts: a right angle triangle, a rectangle, and again a right angle triangle. So now, since we have some unknown parameters, let's just take AM as X. So let AM be X and let Y be, rather let NB be Y. So basically in this trapezium, as you can see, AM is X. So in that case, the length of MN, which is exactly equal to CD, because it is forming a rectangle. And why it is forming a rectangle? Because as you can see, perpendiculars are dropped and the lines AB and CD are parallel to each other, and since they are parallel, the other two angles of that quadrilateral are also 90 degrees, so that becomes a rectangle, and therefore CD is going to be equal to MN, and that is why CD is equal to A and MN is equal to A. So now let AM be X, let MN, and hence MN is equal to A, and NB be equal to Y. So we have all the lengths registered here in this particular trapezium. Now let's move on to the area. So area of this trapezium is nothing but area of the right angle triangle AMD plus area of the rectangle MNCD plus area of the right angle triangle BNC. So this is equal to half into H into X, or rather by the formula half into base into height, it is half into X into H plus the area of the rectangle, which is nothing but length into breadth. So in this case, as you can see, this is nothing but A into H, and finally the area of the last right angle triangle is half into Y into H. So now from these three terms, you can take H common, you can take a half into H common rather. So once you do that, what is left in the bracket is you have X plus, now since you have taken a half more, you will have X plus 2A plus Y. Now X plus Y plus 2A is in the bracket, and outside you have half into H. So in the bracket you have X plus Y plus 2A, which can now be written as X plus Y plus A plus A. Now X plus Y plus A is nothing but B. So what is left in the bracket now is B plus A. So the final formula is half into H into B plus A. So we can generalize this formula now as area of trapezium is half into sum of its parallel sides into height, which is what we had exactly learned in the previous chapter of triangles and quadrilaterals. So generalizing area of a trapezium, half into B plus A into H, so half into sum of parallel sides into height. So this is for a trapezium. This is how we found out the area of a trapezium using the areas of a rectangle and two right angle triangles. Now let's talk about a general quadrilateral, right? Now as you can see, we have a general quadrilateral ABCD out here. This is not a specific quadrilateral at all. Now what we are doing here is connecting the points A and C. So once we connect the points A and C, we have a diagonal AC. Now again, using the concept that the quadrilateral is split into two triangles now. One of the triangles is ABC, as you can see, and the other triangles is ADC. So in this triangle ABC, the base is AC, then we drop a perpendicular from B onto AC. Likewise, we will drop a perpendicular from D onto AC. The height, corresponding height here, let that be H1, and here let that be H2. So area of this quadrilateral is nothing but area of the triangle ABC plus the area of the triangle ADC. So that is going to be equal to half into AC into H1 plus half into AC into H2. So taking half into AC common, we'll be left with H1 plus H2 in the bracket. So the formula, general formula for the area of quadrilateral will be half into length of one of its diagonals into the sum of the height of the perpendiculars onto that diagonal. This is how you can write this formula. So you can obviously take BD as the other diagonal and write the same area with respect to BD as the diagonal, but you would need those heights, the new heights. In that case they might be let's say H3 and H4 depending on how you are dropping onto which base. So the basic context of this particular thing is area of a general quadrilateral is nothing but half into length of a diagonal into the product, rather into the sum of the perpendiculars dropped onto that particular diagonal. So this is how we have used the formulas of areas of triangles which we have learned to find out different areas of different quadrilaterals. Further, let's understand the same areas and few theorems about parallelogram in general. So friends, as I said, now we will be talking about areas of a parallelogram. So imagine a parallelogram here. This parallelogram is parallelogram ABCD. Now, if I connect the two opposite vertices, as you can see, AC is the diagonal. So, this parallelogram is now split into two triangles. One being the triangle ABC and another being triangle ADC. So, in the first triangle, the area of that triangle is going to be half into the base AB into its corresponding height. Now likewise, the area of the other triangle is going to be half into its base CD into its corresponding height. So now if I try to find the area of the parallelogram, the area of this parallelogram is going to be the addition of the areas of the two triangles. So that is going to be half into AB into height plus half into CD into height. Now why am I saying height same in both the cases? Reason being, for this particular parallelogram, the height is going to be same for both the triangles, and when we take half into height outside, we will realize that what we are left with is AB plus CD, and then AB and CD both are same entities because opposite sides of a parallelogram are equal to each other. So we can write AB plus CD as 2 times AB, or we can write that as 2 times base, and that 2 is going to cancel with the half in the denominator, and ultimately the area of the parallelogram is going to be just base into height. So whichever base you take for the parallelogram, its corresponding height has to be multiplied with the base to give you the area of the parallelogram. So the conclusion for the area of a parallelogram, the area is equal to base into its corresponding height. So whichever base you take, you have to find its corresponding height and multiply it to the base to get the area of a parallelogram. So after understanding this concept of area of a parallelogram, let's try and understand what happens when we have a base of a parallelogram intact and try to move the above 2 points in a parallelogram, like in this particular figure. Now as you can see here, we have the base AB intact. So the base AB is intact, and I'm trying to draw a parallelogram ABCD, and at the same time we are drawing a parallelogram ABEF. So as you can see, we have two different parallelograms naturally, but both these parallelograms have the same base, which is AB. Now, if you understand, using this particular formula of area of a parallelogram is base into height, if we try and apply that formula directly here, you will get it directly that area of both these parallelograms ABCD and ABEF are going to be exactly same, because the area formula is base into height, and base for both these areas is AB, which is same. And in fact, if you look at it, the height is also same, because both these parallelograms are between the same two parallels, and that is why the height is also same for both of them, and hence the area for both these parallelograms is going to be absolutely equal. So the conclusion here is, if we have the same base, rather if we have a base intact for a parallelogram, and if we keep the above 2 points moving, like this particular visual, as you can see, we can keep the above 2 points moving anywhere you want. The area is still going to be the same, because since the parallelogram is stuck between two parallels, the height is also same, and we are keeping the base as well same. So the area, which is base into height, is going to remain same. Now for this particular case, we can look at this through a different perspective as well. We can bring in the triangles, the two triangles. As you can see, one triangle you can figure it out, it is the triangle DAF, and the other triangle is the triangle CBE. Now we can prove these two triangles congruent. How? We can prove these two triangles congruent by using the SAS test of congruency. We can prove that the side AF is equal to the side BE. Why? Because they are the opposite sides of the parallelogram ABEF. Likewise, we can prove that the side AD is equal to the side BC. Again, because they are the opposite sides of a parallelogram ABCD. And at the same time, we can prove that the angle DAF is equal to the angle CBE, because they are corresponding angles. So now, by SAS test, these two triangles are congruent, and hence we can use the CP/CTC rule and say that DF is equal to CE. Once that is done, we know very well that area of the triangle DAF is going to be equal to the area of the triangle CBE, because both of them have the same height and they have the same base, which is DF is equal to CE. Now, the area of the parallelogram ABCD is nothing but area of the triangle CBE plus the common area ABED. And likewise, the area of the parallelogram ABEF is nothing but the area ABED plus the area of the triangle DAF. And hence, the area of both these parallelograms are going to be equal, because both of them have that common area and the area of the triangle which both of them have equal. So that is another perspective of proving the same thing, that if we have a common base and if the parallelogram is stuck between two parallels, the area of a parallelogram is same, and that is base into height.